Hi guys, Miss Kolova here, about to teach you the right-hand rule. What the right-hand rule does is it tells us either the direction of the magnetic field around a wire or the force exerted on a current carrying wire when it's exposed to an external magnetic field. So first up, we're going to determine this is like the most basic right-hand rule. Start with the basics, right? There we go. All right, so here we have different current carrying wires. Last class, or a couple classes ago, we should have went over different magnetic field symbols. So if we can have current going to the right and current symbols. We can have arrows going to the right, left, up, or down, right, like normal directions that we're used to. And the only difference when we entered this electromagnetism unit is that we have this symbol now, the dot, and we have this X symbol now. What this means, as a reminder, is it means that the direction of the current I is out of the page, so out, and the X means in. So whenever you see a dot, it means that the direction is out, and then whenever you see an X, it means that the direction is in. The reason why we do this is because we need to represent things three-dimensionally now. No longer do we just have X and Y, we have X, Y, and Z, essentially. Okay, so what we're going to do, take off this hat, it's like making me hot. Okay, so for determining the direction of the magnetic field around a current carrying wire, the first step we're going to do is take our thumb and point it in the direction of the current. So here I have arrows going to the right, and I think from your perspective it'll look like it's going to the left. I apologize for that, but here we are. So if you want to draw this out on a sheet of paper, I'll say in words like what's actually drawn, and you can follow along with me if that helps you. So our thumb points in the direction of I, current, conventional current, and then our fingers wrap around the direction of the magnetic field. So right now we have behind the wire, imagine you're holding the actual wire in your palm, right? And it's coming out of the board on top of the wire and going back into the board on the bottom. So right out, in, just so I know. So remember, our out symbol for magnetic field or current, right, is a dot. So I'm going to draw dots. You don't have to put the circle around it if you don't want to, but you can if you like, whatever you prefer. As long as there's a dot, that's all that really matters. That's better. Okay, so we have out of the board on top of the wire, and then we have magnetic field going in on the bottom of the wire. And just so I know that this pink color represents magnetic field, I'm going to write B. So just as a reminder, thumb goes in the direction of the current. Imagine you're holding the wire, right? I'm going to use the marker. Above the wire, magnetic field is coming out, and below the wire, magnetic field is going in to the board. So we're good with that one. That's showing us the direction of the magnetic field around that wire. And let's look at this wire. Same thing, except now the current's flowing to the left. So I'm going to move over here so it's easier for me to work with. And I curl my fingers. It's going out of the board on the bottom of the wire now and into the board on the top of the wire. So out on the bottom means I got to put some dots. And into means I got to put some X's. Okay, and now let's look at the next four examples. I'm going to go a little bit more quickly through these since it's the same process over and over again, except just with different examples. So with this one, we have current flowing up, which means that the magnetic field on the right side of the wire, right, is going to be going into the board, and behind the wire, it's going to be coming back out. So we have into on the right side, and then we have out of the board on the left side. There, let's see that. I'm just drawing dots. Okay, let's do this one now. The current is flowing down, so I'm going to point my thumb down. Imagine like I'm holding the wire. On this side of the wire, magnetic field is going to be pointing out of the board, and on the other side of the wire, on this side of the wire, it's going to be pointing back in. So we have in, and we have out. Doesn't really matter how much dots or X's we draw. I'm not really concerned with that. I'm just concerned with whether it's a dot, an X, left, right arrow, up, down, whatever. So that would be sufficient. And then if we have current, we can have current be three-dimensional as well. So if we have a current, imagine a wire that's pointing out of the page like this, that means my thumb goes out of the board and I have magnetic field wrapping around counterclockwise. Because that's the way that my fingers curl, counterclockwise. So B, so label that. And then the same, another example, so now the current is going to be going into the board. So I have current going into the board, and sounds like Macy is running away. That's not good. So we have a wire with the conventional current going into the board now. So I'm going to point my thumb into the board, and my hand, the way my fingers naturally curl around it, is the direction of the magnetic field, which is going to be pointing clockwise now. Just so I know. And that's how you find the direction of the magnetic field around a current carrying wire. I'll probably label this part 1. I didn't really expect to talk that long. But I'll label this part 1 on YouTube, and then part 2 on YouTube is going to be going through how to determine the direction of the force on a current carrying wire when it's exposed to an external magnetic field.